The Moon looks like the obvious next step. It is the closest world to us, 3 days away. We have already been there, 6 times, 12 people, the last time in December 1972. We know it exists, that it is solid, that you can stand on it. It is visible every clear night without a telescope. By human standards, within reach. NASA is planning to return, the Artemis program, the first humans on the Moon after a half-century gap. Then a permanent base. Then the Moon as a stepping stone to Mars. It sounds like the logical next step in the exploration of space, but there are details that rarely come up in news coverage of lunar programs, specific physical, medical details about what actually happens to the human body on the Moon, about what the lunar surface is actually like, not in the sense of beautiful photographs, but in the sense of the daily physical reality of existing there, about why some problems of lunar life are not just inconveniences, but fundamental challenges we have not yet solved. The Moon is not simply Earth with different gravity and no air. It is a different world, with a specific set of threats that add up to a picture significantly harsher than intuition suggests when you look at it in the night sky. Tonight, we are going to examine this honestly, without exaggeration in either direction. Not to say that the Moon is unreachable, it is reachable and we will return, but to understand what is actually waiting there, what it means to live on the Moon, not to visit for a few hours like the Apollo missions, but to exist there for weeks, months, possibly years. If the night is long, stay. Let us begin with the most obvious and yet least fully appreciated fact about the Moon, its gravity. Surface gravity on the Moon is about 1/6 of Earth's, more precisely 0.165 g. This means that if you weigh 80 kilograms on Earth, on the Moon you would weigh the equivalent of about 13 kilograms. You can jump much higher. Things fall more slowly. Every movement requires less muscular effort. This sounds appealing. In practice, it is one of the most serious medical problems for extended stays on the Moon. The human body evolved in 1G conditions. Every system of the body is tuned to function at this gravity. Bones continuously remodel. Osteoclasts break down old bone tissue, osteoblasts build new, and the balance of this process is partly determined by the mechanical load the skeleton experiences. Under 1G, this load is constant and substantial. Under 0.165 G, the mechanical load on the skeleton drops sharply. The body receives a signal that such a massive skeleton is not needed and begins losing bone mass. This is not a hypothesis, it is a well-documented phenomenon in astronauts on the International Space Station. In microgravity, bone loss rates run about 1 to 2% per month in key regions, the femur, spine and pelvis. On the Moon, at 1/6 G, loss will be less than in weightlessness, but significantly more than 0. 6 months on the Moon without adequate countermeasures, and you risk returning to Earth with a skeleton substantially more fragile than the one you left with. The risk of fractures under ordinary loads increases considerably. Muscles degrade similarly. Under reduced gravity, muscle fibers atrophy. The body does not maintain muscle mass that is not needed to overcome gravity. On the ISS, astronauts spend about 2 to 2.5 hours daily on physical exercise, specifically to counteract this atrophy, and still return with noticeable muscle loss. The cardiovascular system also responds to reduced gravity. The heart works against less pressure. It does not need to pump blood as actively upward to the brain. Over time, the cardiac muscle becomes less conditioned. The redistribution of fluids in the body, blood and lymph shift toward the upper body under reduced gravity, causes characteristic facial swelling and reduced plasma volume. The vestibular system, The balance system in the ear functions under altered conditions. Adapting to 1/6 G takes time. On return to Earth, readaptation to 1G also takes time and can be accompanied by coordination disturbances. All of this is addressable, partially. Proper exercise, specialized loading suits that create artificial load on the skeleton, pharmacological agents that slow bone loss. But none of these solutions is complete. None makes reduced gravity equivalent to Earth gravity from a physiological standpoint. This is the first fundamental challenge of lunar life. Not a catastrophe, but a constant medical reality that needs to be actively compensated for every day. Let us now talk about the lunar day and lunar night, because this is what is most immediately strange about the experience of living on the Moon. The Moon rotates on its axis in about 27.3 Earth days, the same period as its orbit around Earth, since it is tidally locked. This means one complete day-night cycle on the Moon lasts about 29.5 Earth days, the synodic period of the Moon. The lunar day lasts about 14.75 Earth days. The lunar night also about 14.75 Earth days. Nearly 2 Earth weeks of continuous day. Nearly 2 Earth weeks of continuous night. During the lunar day, the Sun slowly crawls across the sky. Its angular velocity is so small that it is practically stationary compared to what our eyes expect. In 1 hour it shifts about 0.5 degrees, equal to its angular diameter. Over 1 hour the Sun shifts by exactly 1 solar diameter, moving but perceived as virtually standing still. Surface temperature during the lunar day gradually builds up. In equatorial regions, the daytime surface temperature reaches about plus 127 degrees Celsius, above the boiling point of water. Then comes the lunar night. Within a few hours near the terminator, the line between the illuminated and unilluminated parts, the surface temperature drops catastrophically. Without an atmosphere to retain heat, the surface radiates its accumulated warmth directly into space. By the middle of the lunar night, equatorial surface temperature reaches about minus 173 degrees Celsius. The temperature swing between day and night, about 300 degrees Celsius. For comparison, the most extreme temperature swing recorded in a single day on Earth, a few dozen degrees. On the Moon, 300 degrees, slowly but inexorably. For the structural materials of a lunar base, this means extreme thermal loads. Materials expand when heated and contract when cooled. Repeated cycles from plus 127 to minus 173 and back will create thermal fatigue in any material. Joints crack. Seals wear. Bolts loosen. Thermal insulation is critically important, but at such temperature differentials, no insulation is trivial. The lunar night creates a power problem. Solar panels that work excellently during the lunar day produce nothing for 2 Earth weeks of lunar night. The base needs an energy source capable of meeting all its needs: lighting, heating, life support, equipment, for 2 Earth weeks without sunlight. Battery storage for 2 Earth weeks of energy, enormous mass and volume. A nuclear reactor is a more realistic solution, a compact source of constant power independent of sunlight. NASA is developing exactly such systems, the Fission Surface Power Program. But this adds significant complexity and cost to lunar infrastructure. One possible way around the lunar night problem is the choice of base location. The poles of the Moon, particularly the South Pole, contain mountain peaks that are in almost continuous sunlight due to the geometry of the Moon's rotation axis. So-called peaks of eternal light receive solar illumination about 80 to 90% of the time. This is precisely why NASA and ESA are considering the South Pole as the preferred location for the first lunar base. But even at the poles, not 100% illumination. Periods of shadow still occur, and the temperature contrast between illuminated and shadowed zones near a pole can be no less severe than on the equator. Let us now talk about what is perhaps the least discussed but most insidious physical problem of lunar life: lunar dust. The surface of the Moon is covered by a layer of material called regolith, ground-up rock formed by billions of years of meteorite impacts. The uppermost layer of regolith, sometimes called the megaregolith, consists of particles of very varied size, from large fragments to the finest dust particles. Lunar dust is extraordinarily fine. Particles smaller than 20 microns, invisible to the naked eye, small enough to reach deep into the lungs, make up a significant fraction of the surface material. For comparison, the diameter of a human hair is about 70 microns. Lunar dust is 3 times finer. But it is not just the size that makes lunar dust dangerous. On Earth, fine dust particles gradually acquire a rounded, smooth shape over time, through abrasion in wind, through water weathering, through contact with other particles. Lunar dust has never been through these processes. It forms only through impacts and through the effects of cosmic radiation and the solar wind. Under an electron microscope, lunar dust particles look like shards of glass, sharp, angular, with jagged edges, like the tiniest fragments of broken glass. Inhaling such particles into the lungs is not just contamination, it is a potentially serious medical threat. Apollo astronauts spent hours on the lunar surface. They returned to the lunar module with dust on their suits. Inside the module, dust got into the air. Several astronauts noted symptoms resembling hay fever, irritation of the nose, throat, and eyes. Harrison Schmitt, Apollo 17, experienced the most pronounced symptoms. He had a known allergy and reacted most acutely to dust contact. That was after stays of a few days. For a permanent base with months or years of exposure, the question of long-term effects of lunar dust on the lungs is open and concerning. The analogy with silicosis, the occupational disease of miners inhaling quartz dust, is incomplete but instructive. Fine, sharp particles in the lungs over time cause inflammation and scarring of the tissue. Lunar dust is also a problem for equipment. Particles become electrostatically charged through photoionization from solar ultraviolet and through interaction with the solar wind. Charged dust clings to surfaces, to the glass of helmets reducing visibility, to solar panels reducing their efficiency, to mechanical joints causing wear, to airlock seals compromising their integrity. Apollo astronauts found lunar dust penetrating everywhere, through seemingly closed gaps, into spacesuit mechanisms, into the ventilation system. Over a few days of presence, the problem was manageable. For a permanent base, dust is a chronic engineering and medical challenge without a simple solution. Let us now talk about radiation, because this is one of the most critical threats of lunar life, and one about which least is said in public discussions of lunar programs. Earth is protected from most cosmic radiation by 2 barriers. The first, the magnetosphere, Earth's magnetic field which deflects charged particles from the solar wind and most galactic cosmic rays. The second, the atmosphere, a layer with mass equivalent to roughly 10 meters of water, which absorbs high-energy particles. On the Moon, there is neither. The Moon has no global magnetic field. There are only weak, local magnetic anomalies. The Moon's atmosphere is so thin it barely exists as a protective layer. The pressure of the lunar atmosphere is 1 trillion times less than Earth's. This means the lunar surface receives the full dose of cosmic radiation without any natural shielding. There are several radiation sources. First, galactic cosmic rays. High-energy protons and atomic nuclei flying from the depths of the galaxy at speeds near the speed of light. They are constant. The flux does not change substantially over time. On the lunar surface, the dose from galactic cosmic rays is about 380 millisieverts per year. For comparison, the annual effective radiation dose for an Earth resident is about 3 millisieverts. On the Moon, from background cosmic rays alone, more than 100 times higher. Second source, solar energetic particles. During solar flares and coronal mass ejections, the Sun expels streams of high-energy particles. These events are unpredictable. They can happen at any time. A major solar energetic particle event without adequate shielding carries doses potentially capable of causing acute radiation sickness, nausea, vomiting, suppression of blood cell formation at very high doses, a threat to life. In August 1972, between the Apollo 16 and Apollo 17 expeditions, one of the largest recorded solar energetic particle events occurred. If astronauts had been on the Moon at that time without adequate shielding, they would have received a radiation dose sufficient for severe radiation injury. Protection from radiation on the Moon requires physical mass. Several meters of lunar regolith piled on top of habitation structures provides significant shielding. This is precisely why lunar-based designs consider underground structures, or structures covered with regolith, as the most realistic architectural solutions. But even with shielding, neutralizing radiation completely is impossible. High-energy galactic cosmic rays interacting with the shielding layer produce secondary particles, a cascade of neutrons and other products that may be no less biologically active than the primary radiation. The optimal thickness and composition of shielding is a subject of active engineering research. The long-term effects of elevated radiation exposure, increased cancer risk, possible accelerated aging, cognitive effects, DNA damage, are medical realities that must be accounted for in planning extended lunar presence. Let us now talk about the absence of atmosphere and what it means beyond the obvious fact that you cannot breathe on the Moon. The absence of atmosphere means the absence of light scattering. On Earth, the sky is blue because the atmosphere scatters sunlight. Short wavelengths, blue, scatter more strongly than long ones, red. On the Moon, there is no scattering at all. The sky is always absolutely black, even at noon when the sun is directly overhead. This creates a striking visual effect, a bright sun against an absolutely black sky. Surface illumination at lunar noon is roughly the same as on Earth on a sunny day, because the Moon is at the same distance from the Sun as Earth. But shadows on the Moon are absolute. Where direct sunlight does not reach, the darkness is complete. This creates a serious visibility problem. Apollo astronauts reported that it was extremely difficult to judge distance and surface relief in the absence of atmospheric scattering. A rock lying in shadow looks like a hole, absolute darkness without gradations. Terrain irregularities that should be visible through shadows are difficult to assess because the shadows are sharp and high contrast rather than gradual and informative. Moving across the lunar surface is visually significantly more difficult than it seems from looking at NASA photographs taken in optimal lighting. At certain illumination angles, especially with a low sun near the terminator, the surface can look flat and nearly featureless despite significant relief. The absence of atmosphere also means the absence of sound. Absolute silence on the lunar surface. Not just quiet, absolutely nothing. There are no sound waves for anything to propagate through. Astronauts in suits hear their own breathing, the mechanical sounds of the suit, radio communication, but nothing from the outside world. This is a psychologically significant experience, difficult to fully comprehend without experiencing it. Humans evolved in an environment rich in acoustic information. Absolute silence is atypical for human experience and can be disorienting. The absence of atmosphere means no weather in the terrestrial sense. No wind, no precipitation, no clouds. But there is a meteorite hazard. On Earth, most meteorites burn up in the atmosphere. On the Moon, any body arriving from space reaches the surface. Most are microscopic, micrometeorites, fractions of a millimeter in size. But even they have kinetic energy sufficient to damage a spacesuit or equipment with a direct hit. For a permanent base, the statistical probability of damage from micrometeorite strikes is a real engineering parameter. Let us now talk about water, because this is one of the most discussed resources on the Moon, and the story here is simultaneously encouraging and more complex than often presented. In 2009, the LCROSS probe deliberately crashed into a permanently shadowed crater near the Moon's south pole, Cabeus crater. Analysis of the ejected material confirmed the presence of water ice. Subsequent missions and remote observations refined the estimates. Water ice is present in permanently shadowed craters near both poles at concentrations ranging from trace amounts to several % by mass. This is good news. Water on the Moon means a potential source of drinking water, water for agricultural needs, and, through electrolysis, hydrogen and oxygen for rocket propellant. The prospect of extracting water on the Moon instead of delivering it from Earth is a key element of the concept of sustainable lunar presence. But the details are more complex. Permanently shadowed craters are among the coldest places in the solar system. In Cabeus crater, the temperature is about minus 240 degrees Celsius, about 33 Kelvin, close to absolute zero. So cold that any volatiles, water, carbon dioxide, ammonia, that arrived there over billions of years, settle and freeze without evaporating. Extracting ice from a permanently shadowed crater at minus 240 degrees is an extremely difficult engineering task. Mining equipment must work at these temperatures. Electronics freeze, mechanical parts lose lubrication, cables become brittle. Moreover, the concentration of ice in the regolith is uneven. In some places, ice is present in significant quantities. In others, only in trace concentrations. Detailed mapping of the distribution of water ice near the South Pole is a task that the Viper rover mission was designed to perform. Even with accessible ice, it needs to be extracted, melted, purified, regolith contains various impurities, and either used directly or decomposed into hydrogen and oxygen. Each step requires energy and equipment. Estimates suggest that creating a fully self-sustaining lunar water system will require substantial initial infrastructure, which still has to be delivered from Earth. A closed cycle is achievable, but not immediately and not cheaply. Let us now talk about the psychological side of lunar life, because this is an aspect that comes up far less often in technical discussions than radiation or dust, but which is no less a real challenge. Imagine a specific situation. You live on a lunar base. Outside, absolute silence. The sky is always black. The landscape changes only slightly. Grey rocks, grey regolith, grey craters. No trees, no animals, no wind, no rain. No variety of smells. Nothing that changes on its own without human intervention. During the lunar day, about 2 Earth weeks, the sun crawls across the black sky practically stationary. There is no 24-hour day-night cycle. The body's biological clock receives none of its familiar synchronization signals. No dawn, no dusk, no natural change in lighting. The human circadian rhythm, the wakefulness and sleep cycle, naturally synchronizes with the daily cycle through visual signals and other external markers. On the Moon, these markers are absent. Maintaining a 24-hour schedule will have to be done artificially. through controlled lighting inside the base, through strict daily routines, through social interaction. This is not just inconvenience. Disruption of circadian rhythm has specific medical consequences. Chronic mismatch between the biological clock and the external environment is associated with increased risk of metabolic disorders, immune dysfunction, deterioration of cognitive function, and psychological disturbances. Studies of polar winter workers, people spending months in polar night conditions, provide useful analogies. Characteristic patterns of depression, irritability, concentration difficulties. The isolation at a lunar base will be significantly more complete than any other isolation in the history of human experience, except extended spaceflight. At a polar station, a person is isolated but is on Earth. Theoretically, evacuation is possible. There is a sky that changes color. There is wind. There are animals. On the Moon, complete isolation from everything biospheric. Not a single organism other than the people on the base and the microbes they bring with them. No living things outside, no nature in any familiar sense. The crew will work in very limited space. Whatever the reasonable volume solution, it will be incomparably smaller than even the smallest town. With the same people in the same rooms, day after day, week after week. Interpersonal conflicts in such conditions are practically inevitable. Research on submarine crews, polar station workers, long-duration ISS expeditions all indicate that interpersonal relationships are among the most significant stressors. Irritation from a neighbour's habits, accumulated grievances, conflicts over different working styles. In conditions where it is impossible to physically go somewhere far away, these factors intensify. Add to this the communication delay with Earth. Not critical as for deep planetary missions, the delay is about 1.3 seconds one way, but sufficient that real-time communication feels slightly unnatural. A video call with a 2.8-second round-trip delay, noticeable. And the impossibility of immediately physically meeting with loved ones on Earth. Psychological selection and crew training is a critical component of extended lunar missions. But selection does not eliminate the problem, it only reduces the probability of the most acute crises. Let us now talk about the specific engineering challenge that is one of the most complex for extended lunar presence, about the reliability of life support systems in conditions where failure means death. On the ISS, if something goes wrong, in most cases the crew can evacuate to Earth within a few hours. Soyuz capsules are permanently docked as lifeboats. Despite being in vacuum at 400 kilometers altitude, Earth is a few hours away. On the Moon, the situation is fundamentally different. Return to Earth requires preparation, fueling, an optimal launch window. This is not an emergency evacuation in a few hours. Depending on specific circumstances, it could take days. This means all life support systems must either be exceptionally reliable or have redundancy, backup systems capable of taking over the functions of the primary if it fails. The air regeneration system, the water supply system, the thermal regulation system, the pressure maintenance system. Seal failure, depressurization of the habitation module, is a scenario requiring immediate response and absolutely reliable backup solutions. On the ISS, procedures have been worked out. On a lunar base, analogous procedures are needed, but under conditions of greater distance from Earth and potentially a smaller crew. Lunar dust again appears here as an engineering threat. It gets into mechanisms and airlock seals. Constant intrusion of lunar dust into mechanical joints causes abrasive wear. Seals that in laboratory conditions last years, on a lunar base may wear out significantly faster due to constant contact with sharp regolith particles. Maintenance on the Moon is fundamentally more complex than on Earth, or even on the ISS. Working in a spacesuit reduces hand dexterity roughly to the level of a person wearing heavy winter gloves, but worse. Tightening a small bolt in suit gloves is significantly more difficult than without them. Component replacement, equipment repair, troubleshooting, all of this takes longer, requires more effort, and involves greater risk of error. And spare parts. Everything that can break must either be kept in stock or be producible on site. Delivery from Earth takes time and costs colossal amounts of money. For the first lunar bases, the ability to independently manufacture spare parts will be limited. 3D printing from lunar regolith and recycled materials is one research direction. But for complex electronic components, precision mechanical parts, specialized medical consumables, delivery from Earth remains a necessity. Let us now talk about food, because providing nutrition for extended lunar presence is a significantly more complex task than simply delivering enough canned food. For short missions, a few weeks, a supply of prepared food is a realistic solution. ISS astronauts receive food from Earth in regular cargo missions. For a lunar base in the early years, the same, but for extended independent presence, food must be produced on site. Bringing a food supply for several people for years in advance, enormous cargo mass. At estimated delivery costs to the Moon of hundreds of thousands of dollars per kilogram, this is an untenable expense. Lunar agriculture, growing food on the Moon, is theoretically possible, but practically extremely difficult. Gravity at 1/6 g affects plant growth. Studies in microgravity on the ISS show that plants can grow under significantly reduced gravity, but some biological processes change. How specifically plants adapt to 1/6 g is a subject of current research. Illumination for photosynthesis requires energy. During the lunar day, sunlight is available, but will require redirection and concentration systems for greenhouses. During the lunar night, artificial lighting will require substantial energy expenditure. The soil problem. Lunar regolith is not soil in the biological sense. It contains no organic matter, no soil microorganisms, no humus. Germinating seeds in pure regolith is very difficult, though experiments have shown that with added nutrients, certain plants can grow in regolith-like substrates. Hydroponics and aeroponics, growing plants in nutrient solutions without soil, are more realistic approaches. Water for agriculture. A closed-loop water recycling system is necessary. Water evaporated through plant transpiration must be collected and reused. The diet from what it is possible to grow in first lunar greenhouses will be very limited. A few species of fast-growing crops with high nutrient yield per unit area. Sufficient caloric intake is possible. A fully balanced diet providing all vitamins, minerals, and necessary micronutrients, significantly more difficult. Let us now talk about the psychological significance of something we have not yet discussed, about what the night sky looks like from a lunar base, and what it means for people living there. The Moon has no atmosphere. This means the sky on the Moon is always absolutely black, both day and night. Stars are visible at all times when the sun is not in the field of view or blinding. But the most striking thing about the lunar sky, Earth. From the Moon, Earth is visible as a large disk with an angular diameter of about 2 degrees, roughly 4 times larger than the Moon appears from Earth. Earth has phases, like the Moon seen from Earth. When the Moon is between Earth and the Sun, new Moon from Earth's perspective, Earth is seen from the Moon as a full Earth. When the Moon is behind Earth, full Moon from Earth's perspective, Earth is near the Sun's disk and appears as a thin crescent. From the Moon's surface, Earth is practically stationary in the sky. Since the Moon is tidally locked to Earth and always faces it with the same side, from any point on the near side of the Moon, Earth is always in the same place in the sky. It does not rise or set. It slowly changes phases, but does not change position. For people living on a lunar base, Earth will be a constant reference point, a large blue disk against a black sky, always in the same direction. During the day, difficult to see against the bright sky near the sun. At night, brighter than any star, casting noticeable light. In full Earth phase, the illumination from Earth on the lunar surface is about 50 times stronger than the illumination from a full moon on Earth. A full Earth casts visible shadows on the lunar surface. This constantly hanging blue disk in the sky will have psychological significance for lunar base inhabitants. It is a visual connection to home. At the same time, a constant reminder of distance from home. People react to this differently. Apollo astronauts described the view of Earth from the Moon as a deeply transformative experience. A small blue ball in the black void. All of human history, all familiar beings, everything that matters, in one fragile, glowing object. For permanent residents of a lunar base, this will not be a one-time revelation, but an everyday visual reality. Let us now talk about something that connects all these concrete challenges with the broader question about what permanent lunar presence means for humanity and why it is needed at all. The reasons that come up. The Moon as a scientific laboratory. Astronomical observations from the Moon are free of atmospheric interference. The far side of the Moon is the only place in nearby space completely shielded from radio interference from Earth, making it ideal for radio astronomy and observations of low-frequency radiation from the universe. Lunar regolith contains a record of the solar wind over billions of years, a valuable archive of solar history. A permanent lunar observatory can monitor the sky with continuity and sensitivity unavailable from Earth. The Moon as a stepping stone for deep space. The Moon's weak gravity means launching from the Moon requires significantly less propellant than from Earth. If rocket propellant, hydrogen and oxygen from lunar water, can be produced on the Moon, then the Moon becomes a refueling station for missions to Mars and beyond. The Moon as insurance for humanity. A permanent settlement beyond Earth, even on the Moon, creates a backup of human civilization. If something happens to Earth, a pandemic, an asteroid impact, nuclear war, a lunar colony could preserve human presence and knowledge. The Moon as a technology testbed for Mars. All the technologies needed for permanent lunar presence, ISRU, life support, radiation shielding, long-range communications, are also needed for Mars. The Moon at 3 days away allows testing and improving these technologies with the option of relatively rapid evacuation if necessary. Mars at 6 to 9 months away does not offer this option. All of these reasons are real. None of them makes lunar life easy. They explain why we go there despite the difficulties, not because it is simple, but because it matters. The Moon is not Earth with different gravity, but it is the next step. And that next step, with all its specific difficulties, with dust and radiation and temperature swings and psychological load, that step we are about to take. Let us talk about the specific historical experience of Apollo astronauts on the lunar surface, because we have real data about how people felt there, and this data gives valuable context for understanding what it physically means to be on the Moon. 12 people walked on the Moon. Total time spent on the surface during EVAs, about 80 hours for all missions combined. That is not much. The longest single excursion, Apollo 17, third EVA, about 7 hours 15 minutes. But those hours gave the first real data about how the human body and mind respond to the lunar environment. The first thing nearly all astronauts noted: movement. Walking on the Moon at 1/6 g is strange. Your muscles are calibrated for 1 g. Each step is calculated for 1 g. At 1/6 g, an ordinary step carries you too high and too far. Landing happens more slowly than the brain expects. The first few minutes, adaptation. Astronauts quickly developed a characteristic lunar gait, something between kangaroo bounds and a rapid shuffling step. By bounding, pushing off with both feet simultaneously and floating through small leaps, you can move significantly faster and more efficiently than by trying to walk as on Earth. The Apollo videos show exactly this, characteristic bounding. This is not just fun, it is optimal biomechanics for 1/6 g. Falls. Several astronauts fell during lunar walks. Charlie Duke, Apollo 16, fell several times. At 1/6 g, a fall happens more slowly than on Earth, which reduces injury risk. But the suit is rigid and bulky. Getting up independently is not always easy. The standard technique, roll to the side and then stand. Astronauts practice this before the flight. Orientation on the terrain. Several astronauts noted that the lunar landscape deceives about distances. Without atmospheric haze, without aerial perspective that the brain uses to estimate distance, distant objects appear closer than they are. A crater that seems a few hundred meters away may be several kilometers away. Apollo 14, Shepard and Mitchell, tried to reach Cone Crater. By the calculations, it was about 1.5 kilometers away. They walked toward it much longer than expected. When they were very close, they had to turn back due to time constraints. Later analysis showed they were very close to the crater rim when they turned. Thermal conditions in the suit. Suits with a liquid cooling system, water circulates through a network of tubes in special undergarments beneath the main suit. The system is effective under moderate physical exertion. Under intense work, running, climbing slopes, heavy manual labor, the thermal load increases and astronauts became warmer than comfortable. Some noted they were working at the limits of the cooling system's capacity. Fatigue. Walking in a spacesuit at 1/6 g is physically tiring despite the low weight, because the suit material's resistance creates a constant load with every movement, especially when bending joints. After several hours working on the surface, astronauts returned noticeably tired. Exhilaration. This is important to mention. Virtually all Apollo astronauts described the lunar EVAs as among the most intense and meaningful experiences of their lives, not just as work, as an experience. The landscape, Earth in the sky, the silence, the awareness of where they were. Several described moments when they had to remind themselves to keep working rather than just standing and looking. Harrison Schmitt, the only scientist geologist to walk on the Moon, Apollo 17, described the experience literally as professional happiness. He was on the Moon as a geologist studying rocks. He described the excitement of each rock, each exposure, each terrain detail. Eugene Cernan, the last person to walk on the Moon, described how, before boarding the lunar module for the last time, he wrote his daughter's initials in the lunar dust and thought about how they would remain there for millions of years because nothing would erase them. This is real human experience, real people in a specific place with specific physical sensations and specific emotions. Let us now talk about what has changed in our knowledge of the Moon in the time since Apollo, and what this new knowledge tells us about the realism of long-term lunar presence. During the Apollo period, 1969 to 1972, we collected about 382 kilograms of lunar samples. These samples are still being studied. New analytical methods continue to extract information that was not obtainable earlier. One of the most significant recent discoveries, the detection of traces of water in the lunar soil samples brought back by Apollo. For a long time, it was believed that the Moon was completely dry as a bone. Later, detailed analysis using modern mass spectrometers detected traces of hydroxyl groups, OH, and molecular water in certain lunar minerals. Concentrations are very small, on the order of a few parts per million, but the very presence refutes the assumption of complete dryness. China's Chang'e 5 mission in December 2020 returned 1.73 kilograms of samples from the Mons Rumke area, a young volcanic region. These are the first new lunar samples in 44 years since the Soviet Lunar 24 in 1976. Analysis showed an age of about 1.96 billion years, significantly younger than all Apollo samples, 3 to 4.5 billion years. This extended the known time range of lunar geological activity. The LRO, Lunar Reconnaissance Orbiter, operating since 2009, created detailed maps of the lunar surface at about 0.5 meter resolution, sufficient to see equipment left by Apollo. These maps revealed vertical pits, entrances to possible lava tubes in several regions. Mapping of permanently shadowed craters showed their distribution and ice concentration estimates. India's Chandrayaan-3 in August 2023 became the first mission to successfully land near the Moon's south pole. Its Pragyan rover operated for about 2 weeks, 1 lunar day, and transmitted data on the elemental composition of the surface in the polar region, detecting sulfur, aluminum, calcium, iron, chromium, titanium, manganese, silicon, and oxygen. Japan's SLIM mission in January 2024 became the first Japanese moon landing, though it landed inverted and operated for a limited time. The combined body of this new data has substantially refined our view of the Moon. We know more about the distribution of resources. We better understand the geological history. We have more detailed maps of potential landing sites. But with all of this, we have never studied the Moon as a place for extended human presence with the degree of detail that would be necessary. No spacecraft has conducted long-term measurements of radiation levels on the surface at different locations and during different phases of solar activity. No spacecraft has studied lunar dust dynamics near human activity, vehicle movement, construction work. No spacecraft has studied the geotechnical properties of regolith at potential construction sites at the scale needed for engineering design. This is data we need, and that will be gathered within the Artemis program, starting with its first missions. Let us now talk about the specific medical questions that are most acute for the first lunar missions, about what happens if someone becomes seriously ill or is injured on the Moon. On the ISS, medical care is limited by crew training and onboard equipment. Astronauts undergo basic medical training. The station has a medical kit, a defibrillator, surgical instruments for emergency interventions. In a critical situation, evacuation to Earth in a few hours, on the Moon, the situation is fundamentally different in terms of evacuation speed. Return to Earth will take a minimum of several days. Consider specific scenarios. Scenario 1. Suit depressurization. A small suit damage. A crack in the helmet visor. A cut in the suit material from a sharp rock edge can lead to slow or rapid depressurization. The astronaut has a few hours of air supply. Immediate action: return to the base or to a pressurized module. The distance to the base is critical. Too far and the supply runs out before reaching shelter. This is precisely why the rule of thirds, 1/3 of air out, 1/3 back, 1/3 in reserve, analogous to scuba diving rules, is fundamental for lunar EVAs. Scenario 2. Serious trauma on the surface. A broken leg from falling into a crater. Evacuation of the injured astronaut in a suit, weighing about 120 to 130 kilograms suited up, by one or two crew members in their own suits is a physically extremely difficult task. Special stretchers or emergency transport devices must be part of the base's equipment. Scenario 3. Acute surgical condition. Appendicitis, ruptured aneurysm, intestinal obstruction. On Earth, emergency surgery. On the lunar base, surgical intervention at the base by a crew member with surgical training. Surgery in 16G presents specific challenges. Blood behaves differently under low gravity. Fluids can collect in spherical droplets. Instruments behave differently. The operative field is illuminated differently. This is not simply the same operation, but in a different place. It is a new medical domain. NASA funds research in telesurgery, an operation performed by a specialist on Earth using a robotic manipulator controlled remotely. The signal delay, Earth-Moon, about 1.3 seconds one way, 2.6 seconds round trip, is not critical for telesurgery, unlike the delay for operations on Mars. Telesurgery for lunar missions is a technically feasible prospect. Psychiatric crises. Acute psychosis, severe depression with suicidal ideation, panic disorder in a confined space. These scenarios are not contrived. Analogous situations have occurred in the history of polar expeditions, on submarines, in conditions of prolonged isolation. On a small lunar base, one person in acute psychiatric crisis is a safety threat to the entire crew. All these medical scenarios are being developed and planned for, but planning is not a solution. Many of these situations will have outcomes significantly worse than on Earth, simply because of limited resources and the distance from help. Let us now talk about the specific program that will determine how we return to the Moon, about the Artemis program and what it realistically plans to do. Artemis, NASA's program with the participation of international partners, ESA, JAXA, CSA and others, aims to return people to the Moon. The program structure: Artemis 1, unmanned test flight of SLS/Orion around the Moon, completed in November to December 2022. Successful. Orion spent about 25 days in flight, orbited the Moon, returned to Earth. Artemis 2, crewed lunar flyby without landing, planned with numerous delays. A 4-person crew aboard Orion should orbit the Moon and return to Earth. This will be the first human flight to the Moon since December 1972. As of 2024, planned no earlier than 2025 to 2026. Artemis 3, first moon landing under the program, uses SpaceX's Human Landing System, a modified Starship adapted for moon landing. Landing is planned near the South Pole. First woman on the Moon. As of 2024, planned no earlier than 2026 to 2027. After Artemis 3, subsequent missions are meant to gradually build infrastructure. Lunar Gateway, a small orbital station around the Moon, serving as an intermediate point. Gradual creation of surface assets, habitation modules, rovers, ISRU systems. Long-term concept: by the 2030s, NASA hopes to have a permanent presence on the Moon, Not just short visits like Apollo, but a continuously rotating crew spending weeks and months on the Moon. Is this timeline realistic? Most independent analysts consider it optimistic. The history of space programs shows that delays are the norm rather than the exception. Technical problems, spacesuits, landing systems, gateway, all are running late. Budget constraints are real. Nevertheless, the direction is clear. We are going back to the Moon. The question is not whether, but when exactly, and with what capabilities. And when we return, we will face all those challenges we have discussed. Not because they are insurmountable, but because they are real. Let us now talk about the specific phenomenon that is one of the most important for understanding the lunar surface as a working environment, about the seismic activity of the Moon. Before the Apollo missions, there was uncertainty about whether the Moon was geologically active. The Apollos installed seismographs, sensitive instruments recording seismic waves. They operated until 1977, when they were shut off for budget reasons. The data from these seismographs is still being analysed. It revealed several types of lunar seismic activity. Deep moonquakes occur at depths of about 700 to 1,200 kilometers. They are regular and predictable, occurring in clusters roughly every 27 days, coinciding with the Moon's orbital period. The cause? Tidal forces from Earth. These moonquakes are weak but surprisingly long-lasting. A lunar seismograph rings after them sometimes for hours. This is explained by the fact that the lunar crust is very dry and fractured. Seismic waves scatter slowly. Shallow moonquakes occur at depths up to 200 kilometers, less regular, presumably caused by thermal stress, contraction and expansion of the crust as it passes through the terminator. Some can reach magnitude 5, strong enough to cause structural damage. Meteorite impacts, registered as brief seismic events, provide information about the meteorite flux. Thermal moonquakes occur near sunrise and sunset when the surface temperature rapidly changes, very shallow. Important fact for construction: shallow moonquakes of magnitude up to 5 are a real seismic threat. Any structures on the lunar surface must be designed with seismic loads in mind. On Earth, buildings are constructed in seismically hazardous zones according to special standards. On the Moon, analogous standards need to be developed. The long, ringing response of the lunar crust to seismic events, hours after an impact, means that bases must be able to sustain prolonged vibration. This places requirements not only on load-bearing elements, but on connections, pipelines, and fluid storage systems. Let us now talk about the architecture question more concretely, about the actual options being considered for lunar habitation. The first and most obvious approach: bring habitat modules from Earth. This is planned for the first Artemis missions. Pressurized cylindrical or spherical modules similar to ISS modules, rigid metal structures with good seal integrity, reliable life support systems, proven technology. The problem? Mass. Delivering 1 kilogram of cargo to the lunar surface costs, by various estimates, anywhere from tens of thousands to hundreds of thousands of dollars, depending on the rocket used and the specific mission. A large habitation module, sufficient for several people, weighs several tons. This makes creating a large lunar base from Earth-delivered modules extremely expensive. The second approach: inflatable structures. Bigelow Aerospace developed inflatable habitat modules. One such module, BEAM, Bigelow Expandable Activity Module, was delivered to the ISS in 2016 and has been successfully operating since. Inflatable modules are more compact during transport and expand to a significantly larger volume after inflation. NASA considers inflatable structures a promising solution for lunar habitats. Advantage: larger volume for the same transport mass. Disadvantage: resistance to lunar dust and radiation depends on the shell material. Modern multi-layer shells are robust enough to withstand micrometeorite impacts and provide acceptable radiation shielding, but a less rigid shell creates different structural engineering challenges than a metal module. The third approach, using natural shelters. Vertical pits have been discovered on the Moon, openings leading to subsurface lava tubes. Lava tubes form when the surface of a lava flow solidifies, forming a crust, and the liquid lava continues to flow beneath it, then drains out, leaving a void. On the Moon, due to lower gravity and the absence of an atmosphere, such tubes may be significantly larger than on Earth. Size estimates range from tens of meters to several kilometers in diameter. A lava tube would provide natural shielding from radiation, several meters of basalt rock overhead, from micrometeorites, from temperature swings. The temperature deep in a lava tube is presumably stable and significantly more moderate than on the surface, perhaps around -20 degrees Celsius, which, while cold by Earth standards, is incomparably more stable than the 300-degree swing on the surface. This sounds attractive, a ready-made natural shelter. The problem: we don't know what's inside. Entry into a lava tube through a vertical pit requires special equipment. The tubes may be partially filled with regolith. The geometry may be unfavourable. Engineering work to create a pressurized habitation space inside a lava tube would require substantial effort. The fourth approach: construction from local materials. Lunar regolith is a potential building material. It can be compacted, sintered by heat, used as a component in concrete. 3D printing from regolith, a technology where a controlled machine, layer by layer, deposits sintered regolith creating three-dimensional structures, is an actively researched approach. The most realistic near-term answer for lunar architecture: the first permanent habitable structures will be metal or inflatable modules delivered from Earth, covered by several meters of regolith for radiation shielding. As 3D printing technologies from regolith mature, larger, locally constructed structures will appear. In the very long term, possibly the use of lava tubes. Let us now talk about something that illustrates the gap between public perception and physical reality of the Moon. About what the view from a lunar base actually looks like at different times of the lunar month. During the lunar day, when the sun is above the horizon, step outside and the scene is stark. A black sky with a blinding sun in it. No blue, no haze, no gradations between the lit surface and the dark sky. Just black and white and the colours of the rocks, grey and brown, and occasionally flecked with bright minerals. The horizon appears close. On the Moon, with its smaller diameter, Earth's horizon visible from average height is about 4.7 kilometers away on a flat surface. The lunar horizon is about 2.4 kilometers from standing height on flat terrain, significantly closer than on Earth. The world curves away more quickly because the Moon is smaller. This gives a peculiar visual impression. The horizon seems very near, almost cramped. The world visible to you from any point is a smaller circle than you are accustomed to on Earth. Beyond that close horizon, nothing visible, because the surface curves away. If you are near a mountain or elevated feature, the view extends. The Moon has significant relief, craters, mountain ranges, rills. From the rim of a large crater, you can see across its floor and to the far wall, which may be tens of kilometers away. From a high peak, the view extends to the horizon at greater distance. The quality of light on the lunar surface is extreme. No diffuse light, only direct sunlight or nothing. In the lit areas, every grain of dust casts a shadow. At low sun angles near the terminator, the texture of the surface is extraordinarily revealed by the extreme grazing light. Every small crater, every ripple in the regolith, every pebble casts a sharp shadow many times its own size. The surface looks like a highly detailed relief map illuminated from one side. In shadow, nothing. Complete darkness. Your eyes, fully dark adapted, see essentially nothing in the lunar shadows because there is no reflected light from an atmosphere filling in the shadows. The only light in shadow comes from Earthshine, if Earth is visible and in a phase that provides light, and from starlight. Earthshine in full Earth phase casts enough light to navigate by, but not to see in detail. This alternation between blinding sunlight and absolute shadow on the same surface is visually unlike anything on Earth. It makes moving across the terrain cognitively demanding in a way that neither ordinary daylight nor night with flashlight is, because your eye is forced to work with both extremes simultaneously. Let us now talk about the practical implications of the 1/6 G environment for specific types of work that people on a lunar base would need to do regularly. Consider digging. Lunar regolith must be excavated for various purposes: to provide radiation shielding over habitation modules, to access subsurface ice, to create foundations. In 1/6 G, a shovel load of regolith that would weigh 20 kilograms on Earth weighs only about 3 kilograms. This sounds like easier digging, but the dynamics are different. When you push a shovel into soil on Earth, part of what drives it in is the weight of your body pressing down through the tool. In 1/6 G, you weigh only 1/6 as much. You have only 1/6 the force from body weight to drive the shovel. Digging requires repositioning your technique entirely, using arm strength and leverage rather than body weight. Moving loose regolith, with no atmospheric pressure to help compact it, and different angles of repose than Earth soil, behaves in ways that construction equipment is not calibrated for. Regolith particles are angular and interlock mechanically. In some ways, loose regolith is harder to move than it appears because of this interlocking. In other ways, it is easy to excavate because the material is unlithified. Equipment transport. Moving large objects on the lunar surface requires different approaches than on Earth. The low gravity means objects are light to lift. A 500 kilogram rock on Earth weighs only about 83 kilograms on the Moon. But its inertia is the same. A 500 kilogram rock resists acceleration and deceleration with the same force regardless of gravity. Stopping a moving rock requires just as much force as stopping it on Earth at the same speed. This means that when pushing heavy objects, inertia is the limiting factor rather than weight. Equipment moved carelessly can take a long time to stop. Cargo that starts sliding can be difficult to arrest. New intuitions have to be built for how objects behave in transit. Electrostatics. Because there is no humid atmosphere to bleed off charge, everything on the Moon readily builds up and retains static electricity. Dust sticks to surfaces that are charged oppositely. Tools, instruments, and structure surfaces all develop charge gradients. Metallic objects may need to be grounded regularly to prevent electrostatic discharge events that could damage sensitive electronics. Let us now talk about one of the most significant and least discussed long-term human factors issues for lunar presence, about monotony, and specifically about the kind of monotony that is different from anything previously experienced. The lunar surface is extraordinarily uniform in colour: grey, slightly reddish-grey in places, slightly yellowish-grey in others, but fundamentally and overwhelmingly grey. The rocks are grey, the regolith is grey, The shadows are grey where they have any perceptible shade. The sky is black, the sun is white-yellow. The dominant visual experience of the lunar landscape is an almost total absence of colour. On Earth, colour is a constant source of stimulation. Green vegetation, blue water, brown earth, the constantly changing palette of sky at sunrise and sunset, the colours of flowers, of fruit, of clothing. On the Moon, none of this. The visual environment outside is essentially two-tone, the grey of the sunlit surface and the black of shadow and sky. Inside the base, colour can be provided artificially. Interior design choices can include warm colours, varied lighting, art. But the unchanging monochrome of the exterior will be visible through any window or camera feed, and every EVA will immerse crew members in an environment more visually impoverished than any natural environment humans have evolved to inhabit. Over months, the monotony of this environment may accumulate in ways that are difficult to predict. Research on environments with low visual variety, windowless factories, submarines, polar night, shows that visual monotony contributes to sensory deprivation effects, to a reduction in the sense of time passing coherently, and to a general dulling of motivation. This is not a problem that can be solved by stocking enough movies or books. It is a feature of the environment itself. The people who cope best with visual monotony tend to be those with highly active internal mental lives. Scientists who can be fully absorbed in their research, writers, musicians, people with intense hobbies that generate internal stimulation independent of external input. Selecting crew not just for technical competence, but for psychological characteristics that predict resilience under perceptual monotony is one of the more nuanced challenges in designing long-duration lunar missions. Let us now talk about what specific measurements and experiments will be made on the first Artemis lunar surface missions that directly address the uncertainties we have been discussing. One of the most important science objectives for early Artemis surface missions is characterizing the radiation environment in detail. No previous mission has placed radiation dosimeters on the lunar surface for an extended period in multiple locations. The DOSIS, dose distribution inside the space station instruments on the ISS, have measured radiation inside a pressurized habitat. What is needed for lunar surface mission planning is measurements outside, on the surface, over extended periods, including through at least one solar energetic particle event, so we can understand the dose inside a shielded structure versus outside. Artemis 3 will place radiation measurement instruments on the lunar surface. Later missions will build up a longitudinal record. Dust characterization. Artemis surface missions will collect regolith samples, but also attempt to characterize the behavior of lunar dust in the context of human activity, including how much dust gets disturbed by walking and by landing, and how it settles. Small cameras and particle detectors will try to measure the dust environment near the landing site before, during, and after human EVAs. Geotechnical measurements. How the regolith compacts, how it supports loads, how it behaves when excavated. These measurements are needed to design surface structures, roads, and ISRU equipment. Simple penetrometers and other instruments will characterize the mechanical properties of regolith at specific sites near the South Pole, properties that differ from the equatorial regolith sampled by Apollo, because the polar regolith has experienced very different thermal and radiation environments. Thermal measurements. How rapidly does the surface temperature change near the terminator at the South Pole? How does the temperature vary with depth? These measurements determine insulation requirements for equipment and structures. ISRU demonstrations. The demonstration of actual extraction of oxygen from lunar regolith, even in small quantities, would be a milestone. The MOXIE experiment on the Mars Perseverance rover has demonstrated oxygen production from the Martian atmosphere. An analogous experiment extracting oxygen from lunar regolith on one of the early Artemis missions would be a crucial demonstration. Each of these measurements reduces an uncertainty. The uncertainties are what make planning difficult, or rather, what makes it necessary to plan for the worst case, which is expensive. Better measurements allow more precise planning and potentially less expensive over-engineering. Let us now talk about something that is simultaneously one of the most practically significant and most philosophically interesting aspects of returning to the moon. About the question of what gets left behind and what it means. When Apollo astronauts left the moon, they left behind the lower stages of the lunar modules. These are still there, their exact locations known, their positions on the surface catalogued. The Lunar Reconnaissance Orbiter has photographed them from orbit. These structures sit unchanged in exactly the conditions where they were left more than 50 years ago. In the absence of weathering, in the absence of biological activity, in the absence of any erosion except the slowest possible micrometeorite bombardment, objects on the lunar surface persist essentially unchanged on human timescales. The footprints of the Apollo astronauts, if not disturbed by landing exhaust or future surface activity, may still be visible. This means that the first permanent lunar base will be accumulating a history in a way that no Earth settlement can. A structure built on the moon in the 2030s will still be standing essentially unchanged in the 2130s. A tool set down and not retrieved will be there indefinitely. The material culture of early lunar civilization will be preserved in a way that the material culture of early Earth civilizations was not. This creates an unusual relationship with time. On Earth, cities are built on ruins of previous cities. Structures crumble, materials decay. Nothing lasts more than a few centuries without active maintenance. On the moon, the first generation of human objects may outlast not just their builders, but civilization itself, remaining legible to whoever visits millions of years from now. The astronaut who scratches their name into the lunar regolith, like Cernan wrote his daughter's initials, is writing something that will remain readable not just until their death, but potentially for geological timescales. The erasure timescale for such a mark is millions of years, not years or decades. This is a different relationship with permanence than humans have had access to before. Let us now talk about the concrete comparison that most directly illustrates how different lunar life would be from anything previously experienced, about how the lunar environment compares to the most extreme human environments on Earth. The most commonly used analogy is Antarctic wintering stations. People live there for months in isolation at extreme temperatures with limited evacuation options in winter. Psychological studies of Antarctic winter over cruise have provided valuable data on how humans cope with isolation, monotony, and interpersonal conflict. But the analogy is incomplete. At an Antarctic station, there is an atmosphere. You can go outside without a suit in reasonably good weather. There is a sky that changes colour. There is snow and ice. There are penguins. There is a biosphere outside, however harsh. On the moon, none of this. The degree of isolation from the biosphere is absolute, in a way that no Antarctic station is. Submarines are another analogy. Limited space, extended isolation, inability to exit quickly, dependence on technical systems. The psychology of submarine crews is a valuable data source. But on a submarine, there is Earth gravity. There is a day-night cycle happening outside the hull. There is no radiation threat. There is no lunar dust. There are no 300-degree temperature swings. The ISS is the most relevant analogy. The same microgravity effects, though the Moon's 1/6 g is different from true weightlessness, similar radiation exposure, though the ISS has partial shielding from Earth's magnetosphere, the same isolation in a closed space, the same dependence on life support systems. But on the ISS, there is no lunar dust. There is no need to go out in a suit for routine tasks. Evacuation takes a few hours rather than days. There are regular crew rotations and regular cargo missions. The Moon is something new, not simply the sum of all known analogies. It combines elements of each with additional unique challenges, primarily the dust and the longer autonomy. All of these challenges are surmountable. This is important to emphasize. None of them is a physically insurmountable barrier. Each is an engineering, medical, or psychological problem that is being solved, with sufficient resources, sufficient research, sufficient attention to detail. But the combination of these challenges makes permanent lunar presence a significantly more complex undertaking than it appears when you look at the Moon in a clear night and think, it is so close. It is close, 3 days away, that is true, but being there is something else entirely. Let us talk about something that connects the abstract engineering challenges we have been discussing to a very human reality, about what a typical week on a permanent lunar base might actually look like in terms of daily routine and the texture of life. The rhythm of a week on the lunar base would be shaped by a tension between two competing needs. On one side, the need for structured routine to maintain circadian rhythm and psychological stability in an environment with no natural 24-hour cycle. On the other, the unpredictability of technical issues, EVA conditions, equipment failures, and scientific opportunities that constantly disrupt any planned schedule. A notional week. Monday begins not with sunrise, because there is no sunrise in the 24-hour sense, but with the lighting system shifting from night mode to morning mode at a designated time. The crew assembles for morning health checks, blood pressure, heart rate, sleep quality ratings, cognitive tests, quick assessments that serve both as medical monitoring and as early warning for the psychological deterioration that can accumulate subtly over weeks. Breakfast. Food on a lunar base for the early years will be primarily reconstituted dehydrated food, similar to what ISS astronauts eat, though with improvements over the decades. Fresh food is a morale issue as much as a nutrition issue. Even small quantities of fresh food, a few grams of lettuce grown in a greenhouse module, have disproportionate psychological value on long missions. The first lunar greenhouses would likely prioritize this as much as caloric contribution. The first EVA of the week. Pre-EVA preparation takes an hour or more. Suit checks, briefing, pre-breathe if required, out the airlock. The work today, inspecting the external solar panels, collecting regolith samples from a newly designated site 300 meters from the base, checking the antenna array alignment. Walking 300 meters in a suit at 1/6 g takes longer than it sounds. The bounding gait is efficient but careful. The regolith underfoot is firm in some places, looser in others. Near the base, the surface has been disturbed by previous EVA activity, a fine cloud of regolith particles disturbed and resettled from dozens of previous excursions. Beyond the immediate base perimeter, the surface is undisturbed. Your footprints will be the first ones here. The regolith sample collection is methodical: documentation, photograph, collection, labeling. Then the antenna check. A connector has been showing slightly anomalous readings in telemetry. In the suit, identifying a small connector issue takes 3 times as long as it would at a workbench indoors. The gloves, the limited tactile feedback, the restricted field of view. Eventually found, a thin coating of fine dust has infiltrated the connector housing. Cleaned as well as possible with the tools available. Will need monitoring. Return to the base. Dust removal procedure in the airlock. Suit doffing. Post-EVA medical check and debrief. The afternoon is for laboratory work, sample analysis from today's collection and from previous days. Tuesday, an equipment malfunction. The water recycling system has flagged an anomaly in one of its filtration membranes. The crew member designated as systems engineer begins the diagnostic procedure. Consulting the maintenance manual, which was last updated during training on Earth, and adapting it to the actual conditions. The filtration unit is accessible through a panel in the utility corridor of the base. Tight space. The replacement membrane cartridge is located in the spare parts storage. Assembly and reinstallation. Testing. The system comes back online. 3 hours of the planned science work lost. This is normal. Equipment maintenance on the lunar base is a constant background demand on crew time. Wednesday, an unscheduled communication window with Earth. One of the crew members has a scheduled personal call with family. The 2.6-second round-trip delay makes conversation slightly stilted. Long pauses, accidental interruptions, occasional loss of the natural rhythm of exchange. But the connection is real, the faces are real, and its psychological importance is significant. These calls are protected time, not interrupted for any non-emergency. Thursday, the week's second EVA, a longer one today, to a site about 600 meters from the base. 2 crew members go together. The purpose is geological sampling from a small rill, a linear depression in the surface that may expose layered rock history. Working in pairs has procedural advantages. Each can monitor the other's suit status, help if one gets into difficulty, provide an additional perspective on the scientific observations. The rill, when reached, is about 3 meters wide and 2 meters deep. The walls show distinct layers, the kind of stratigraphic record that geologists find fascinating and that contains information about the history of volcanic activity in this region. Samples are collected from multiple layers. Photography is extensive. On the return, one crew member misses a step in a shallow crater rim and goes down. The slow fall of 1/6 G, landing on one knee and one hand. Suit integrity check immediately. Pressure holding, no breach. Stand up using the practice technique. Brief medical check on radio. Continue. The suit records the impact. When back inside, the suit logs are reviewed and the helmet visor is inspected more carefully for any micro-stress fractures. Found none. Cleared to continue. Friday, indoor focus. The scientific work that has been building up during the week. The geological samples need to be catalogued, described, photographed under laboratory lighting, and selected portions sent through the miniaturized analysis instruments. A subset will be processed in the base's small mass spectrometer. Others will be preserved for eventual return to Earth. Report writing. Each week a summary report goes to Earth, covering health status, equipment status, scientific progress, any anomalies. This report, when it arrives, will be reviewed by teams of specialists who will send questions and guidance back. The 2.6-second round-trip delay means the conversation is asynchronous, more like email than telephone. Saturday, rest day in principle. On the ISS, weekends are scheduled as lighter duty days with some free time. On the lunar base, the same philosophy would apply. But rest on the lunar base is constrained by the environment in ways that rest on Earth is not. You cannot go for a walk outside for the pleasure of it. Every trip outside requires suit up, which takes an hour and carries a not negligible risk. You cannot go anywhere new without planning. You are fundamentally in a small, enclosed space. Recreation within that space, reading, film, music, conversation, games, exercise beyond the minimum required. Some crew members would maintain creative projects, writing, drawing, crafting. Research has consistently shown that people who have engaging hobbies fare better in isolated environments than those who do not. Sunday, maintenance and cleaning. The base accumulates dust. Not lunar dust if the cleaning protocols are effective, but ordinary human-generated particulate matter from skin cells, food preparation, general activity. Filters in the air handling system need regular cleaning. Surfaces that accumulate potential contaminants need wiping. Water system checks, checking the state of the suit hardware. These are the unglamorous tasks that keep the base functional. This week, no medical emergencies, no critical equipment failures, one suit anomaly that resolved without consequence. By lunar base standards, a good week. Let us now talk about the specific question of how the first people who live on the Moon will be chosen, about the selection process and what it implies about who is suited for this. The Artemis program's early surface missions will use astronauts selected through processes broadly similar to existing NASA astronaut selection, with some adaptations. The pool of applicants will be large, the selection very competitive, and the chosen few will have years of training before they set foot on the Moon. But the profile of the person best suited for extended lunar living, months rather than days, is more specific than the profile of a good ISS astronaut, and more specific still than the profile of a good Apollo lunar visitor. Physical resilience under sustained stress, not just the ability to handle an acute crisis, but the capacity to maintain effectiveness week after week in conditions of low novelty, high tedium, and constant background risk. This is a different kind of toughness than what is tested by high-G centrifuge training or emergency scenarios. Emotional self-sufficiency combined with genuine social competence. The lunar crew member needs to be someone who can be genuinely content in their own company for significant periods, who has internal resources to sustain themselves without constant external stimulation, but who can simultaneously be a cooperative, thoughtful, non-abrasive colleague in a small group. These two requirements together are unusual. They select against both extreme extroverts, who need constant social stimulation, and extreme introverts, who find sustained close group living aversive. High tolerance for routine and repetitive tasks performed carefully. Much of what happens on a lunar base is not glamorous. Maintenance, monitoring, documentation, data collection following protocols established months earlier. The excitement of being on the Moon does not persist indefinitely. After a few weeks, the novelty fades, and what is left is work. The work itself must be intrinsically motivating. Excellent physical health without chronic conditions requiring medication, because the supply chain for medications is not reliable enough to depend on for complex or unusual needs, and some medications behave differently under radiation or altered physiology. The medical profile requirements for extended lunar living are more stringent than for ISS in this respect. Deep technical competence combined with broad technical literacy. Each crew member needs to be excellent at their primary role, whether geology, medicine, engineering, biology, and competent across a wide range of secondary skills. The crew of 4 or 6 people on a lunar base collectively need to cover essentially the entire range of skills and knowledge that might be needed. Psychological flexibility, the capacity to adapt when things do not go as planned, to accept that the plan will change, to reframe setbacks as information rather than failures. On the ISS, This flexibility is valuable. On the Moon, where help from Earth is days away rather than hours, it is essential. These characteristics together describe a person who is relatively rare. Finding multiple people with this profile who are also technically qualified and physically fit, and who are compatible with each other, is the real selection challenge for extended lunar missions. Let us now talk about something that rarely comes up in technical discussions of lunar habitation, but that will be one of the most concrete daily realities for anyone living there, about bathing, hygiene, and the management of water for personal use. Water on the Moon will be a precious resource for the foreseeable future. In the early years of a lunar base, before ISRU water production comes online, essentially all water will be delivered from Earth. Even after water extraction from polar ice begins, production rates will be modest. On the ISS today, personal hygiene is managed with a minimal water footprint. There is no shower in the conventional sense. Crew members use pre-moistened towelettes for body wiping, no rinse shampoo for hair, special rinseless dental hygiene products. The total personal water use per person per day on the ISS is substantially less than on Earth. On a lunar base, similar constraints will apply, but with the additional complication that contamination from lunar dust makes the hygiene problem more urgent. Every EVA brings the crew member into contact with potentially harmful dust. Dust removal in the airlock gets most of it, but residual dust on hair and skin after suit doffing is a real concern. A limited water shower, perhaps a few hundred milliliters per wash in a closed-loop system that recovers the water, would address this better than wipes alone. But even this small luxury requires a recycling system for the wastewater, space in the base for a shower facility, and a supply of mild soap that is environmentally compatible with the water recycling chemistry. The cumulative personal hygiene challenge over months of living in a space where proper bathing is difficult tends to affect morale in ways that might seem trivial but turn out not to be. Accounts from Antarctic stations and long-duration submarine patrols consistently note that access to a real shower, even limited, has disproportionate morale value relative to the water and infrastructure it requires. Let us now talk about the specific challenge of communication, not just with Earth, but within the lunar base itself and between crew members on EVA. Communication within the base is straightforward: radio and wired intercom systems, no different in principle from those on the ISS. The small size of the base means face-to-face communication is always an option. Communication on EVA within the immediate base vicinity is similarly straightforward. Suit radio, direct line of sight to the base antenna, standard procedures. The complication begins when EVA routes take crew members over terrain features that block line of sight to the base antenna. A crater rim, a ridge, a significant depression in the terrain. Any of these can create a radio shadow where the crew member's suit antenna cannot reach the base directly. The standard solution is relay antennas, small radio repeaters placed on elevated terrain features around the base perimeter that extend the communication coverage. For routine EVA routes, these can be pre-placed. For exploratory EVAs to new areas, crew members may carry portable relay antennas to deploy as they go, extending their communication reach but adding equipment mass and deployment time. The loss of communication with a crew member on EVA, even briefly, triggers immediate check-in protocols. Communication silence beyond a defined duration triggers emergency procedures. This is not paranoia, but realistic risk management in an environment where a suit problem or fall can become critical within minutes. Earth communication for personal calls is scheduled and protected, but practically constrained by the bandwidth of the communication link between the Moon and Earth. Video calls are possible, but represent a significant bandwidth demand. High bandwidth communication is limited to specific windows when the communication antenna has a clear line of sight to Earth, which, at a South Pole location, is practically continuous since Earth never sets from the near-side South Pole. But the total allocated bandwidth is shared across all mission communication needs: science data downlink, engineering telemetry, voice, video, and personal calls compete with all of these. Let us now talk about a specific question that will determine the long-term viability of lunar presence, about whether it is possible for the human body to recover from extended time on the Moon, and what coming home actually means. Astronauts returning from 6-month ISS missions go through weeks of rehabilitation. The cardiovascular system has adjusted to not needing to pump blood against gravity. The vestibular system has recalibrated to weightlessness. The muscles are weaker. The bones have less density. Walking is difficult. The returned astronaut is escorted not because of protocol, but because they are genuinely at risk of falling in the first hours after landing. For a 6-month lunar mission, the 1/6 G environment means the physiological effects are less severe than after 6 months on the ISS. The skeleton has maintained some loading. The cardiovascular system has continued to work against some gravity gradient. But the bone and muscle losses are real, as we have discussed, and compounded by the radiation exposure during the mission. Return from 6 months on the Moon would likely require a rehabilitation period of several weeks to a few months. Bone density monitoring throughout, supervised exercise reloading, cardiovascular reconditioning, vestibular recalibration. But the specific trajectory of recovery, how long it takes to fully return to pre-mission health baseline, is not known. We have not sent people to 1/6 G for 6 months and then brought them back. The ISS data at 0 G gives an upper bound for the effect. The Moon at 1/6 G is better than 0 G, but how much better is not quantified at 6-month timescales. The possibility that some physiological effects of extended lunar living are not fully reversible is taken seriously. Some bone loss may be permanent even with rehabilitation. Some visual changes seen in ISS astronauts, structural changes to the optic nerve and eye shape from intracranial pressure shifts, have not fully resolved after landing. Whether analogous changes occur at 1/6 G is unknown. This uncertainty is one of the reasons the medical monitoring on the first extended lunar missions will be intensive. Every crew member will be a subject in the most important human physiology study of the decade. Their medical data will directly inform the planning of every subsequent lunar mission. Let us now talk about what the economic reality of lunar presence means for who gets to go and how the base functions. The enormous cost of lunar missions, even with reduced launch costs compared to the Apollo era, means that every person day on the lunar base has an economic value that must be justified. A crew member who is incapacitated by illness, injury, or psychological crisis represents not just a personal tragedy, but an economic loss measured in millions of dollars of mission resources and a reduction in mission productivity. This economic reality shapes the design of everything about the mission. The selection criteria favor people who are unlikely to become a burden on the system. The medical protocols favor prevention over treatment because treatment on the Moon is so much harder than on Earth. The psychological support systems exist not primarily from humanitarian concern, but because a psychologically impaired crew member is an operational risk. This sounds cold when stated directly, but it reflects the reality of operating in an environment where margin for error is genuinely small and consequences of failure genuinely serious. It also shapes what science gets done. Lunar-based science is not open-ended exploration in the way that a research grant on Earth might be. Every EVA, every instrument deployment, every sample collection happens within a framework of pre-approved science objectives that have been prioritized by review committees. The crew execute the science plan rather than freely pursuing curiosity-driven questions. There is room for opportunistic science. If you walk past something unexpected and notable, you are expected to note it and photograph it and report it. But you do not deviate significantly from the planned route to investigate without ground approval, which in practice means hours of delay while the decision works through the asynchronous Earth communication cycle. This constrained mode of science is sometimes frustrating for crew members with scientific backgrounds. The lone geologist who wants to climb that interesting ridge and see what's on the other side, who has to wait for approval, is a real friction between scientific instinct and operational safety. The balance between safe, planned activity and responsive, opportunistic investigation is one of the ongoing design challenges for surface mission operations. Let us now talk about something that looks ahead, about what the Moon looks like not as a destination for the next decade, but as a place for the next century. If the current trajectory of lunar exploration continues, if Artemis leads to a permanent South Pole base in the 2030s, which serves as a foundation for growing infrastructure, what does the Moon look like in 2124? The scenarios range widely. In an optimistic scenario, a lunar settlement of hundreds of people with multiple bases, surface transport routes between them, established ISRU production, greenhouse agriculture, a robust low Earth orbit to lunar surface logistics chain, and the beginnings of lunar industry. In this scenario, the challenges we have discussed, dust, radiation, psychology, physiology, have been addressed through accumulated experience and engineering improvement. Radiation shielding is better, suits have improved dust exclusion. A century of human presence in 1/6 G has produced medical protocols calibrated to this specific environment rather than extrapolated from Earth or ISS data. The psychological challenges are better understood and better managed. In a pessimistic scenario, political and economic pressures on Earth interrupt the sustained investment needed, lunar programs are reduced or cancelled, and the Moon remains a destination visited sporadically rather than permanently inhabited. The challenges prove more stubborn than anticipated. The cost of maintaining permanent presence exceeds what any government or combination of governments is willing to sustain. The realistic outcome is probably somewhere between these. Some sustained presence, a research station analogous to Antarctic stations, cycling crews of dozens rather than hundreds, limited but real ISRU capability, a foundation for future expansion if political will and economic conditions permit. What is clear is that the Moon is not going to be easy to live on in any of these scenarios. The challenges are physical and will remain physical regardless of how much experience we accumulate. Gravity is 1/6 G. Radiation is what it is. The dust is still there. The 2-week night is still there. But the challenges are knowable. They are being studied. The people who will live there will know what they are getting into at a level of detail that the Apollo astronauts, who visited but did not live there, could not know. That knowledge is what separates habitation from exploration. Exploration accepts uncertainty. Habitation works systematically to reduce it. We are in the exploration phase now. The habitation phase is coming. Let us talk about something that connects all the specific challenges we have discussed to a broader question, about what the Moon reveals when we look at it not as a destination, but as a mirror that reflects something back at us about Earth. Every detail of lunar life that is difficult, the radiation, the dust, the psychological isolation, the physiological degradation, is a detail that is difficult because the Moon lacks something Earth has. Magnetic field, atmosphere, biosphere, diurnal cycle in the earthly sense, gravity sufficient for long-term human physiology, the specific chemical and biological environment in which human beings evolved. None of these things were designed. They arose through 4.6 billion years of planetary and biological evolution, each shaping the other in processes so slow and so complex that we cannot fully trace them even with our best science. The magnetic field that protects us from galactic cosmic rays, a consequence of Earth's rotating molten iron outer core, itself a consequence of the specific heat budget of the planet, which is a consequence of the specific mass and composition of the original planetary disk material, which traces back to the particular molecular cloud that collapsed to form the solar system 4.6 billion years ago. Change one parameter early enough and no magnetic field. No magnetic field and the surface radiation environment resembles the Moon's. Complex life, at least the kind that evolved on Earth's surface, probably does not develop. The atmosphere that scatters light, moderates temperature, transmits sound, provides the oxygen we breathe, and burns up meteorites, a consequence of billions of years of outgassing from volcanic activity, of photosynthesis by early cyanobacteria that oxygenated the atmosphere starting about 2.4 billion years ago, of the specific balance between outgassing and escape to space that is set by Earth's mass and surface gravity, and of the specific distance from the Sun that places Earth in the habitable zone. The biosphere that provides the sensory richness, the colours, the sounds, the smells, the variety of forms that humans evolved within, and that the lunar surface completely lacks. A consequence of 3.8 billion years of evolution from the first self-replicating molecules to the current diversity of species. A process that could have gone differently at any of a billion branch points. The lunar base reveals what Earth is by showing what its absence looks like. The 300-degree temperature swing on the Moon reveals what the atmosphere does for us. It moderates temperature, distributing heat in time and in space so that no point on Earth experiences even close to this range in a single cycle. The absolute silence of the lunar surface reveals what the atmosphere does acoustically. It carries the sounds that are so fundamental to human experience that we have barely any language for their absence. The sound of wind, of water, of animals, of other humans at a distance. On the Moon, none of it. The bone loss and muscle atrophy in lunar gravity reveals what Earth's gravity does for our physiology. It provides the constant mechanical loading that our skeletons and muscles are calibrated against. Loading so constant and so fundamental that we need it to remain healthy. The psychological challenges of lunar isolation reveal what the social and ecological richness of Earth does for human mental health. A richness so pervasive and so taken for granted that we have no word for it in the way we have no word for the taste of water. The dust that infiltrates everything reveals what Earth's weathering processes do, grinding angular rock particles into rounded, manageable sediment over time, so that the particulate matter we encounter in daily life is not sharp glass, but rounded grains. Living on the Moon, in a sense, is an education in what Earth is. Each hardship on the Moon is Earth's gift seen from its absence. Let us now talk about one more specific technical challenge that we have not yet fully addressed, about power management on a lunar base, and why it is more complex than simply having a reactor. Energy is the foundational resource on a lunar base. Everything requires it. Life support requires it. Air regeneration, water recycling, thermal control. Lighting requires it. Communications require it. Science instruments require it. EVA suit recharging requires it. ISRU processing requires it. Food production, artificial lighting for greenhouses, pumps for hydroponic systems requires it. Heating during the lunar night requires it. A nuclear fission reactor, the most realistic power source for the long lunar night, provides a baseline of reliable power. The NASA/DOE Kilopower program developed a small fission reactor design producing about 10 kilowatts of electrical power. A lunar base supporting 6 people would realistically need several times this capacity, perhaps 30 to 40 kilowatts for basic operations and more for ISRU processing. But reliable baseline power does not mean unlimited power. Every system that uses power competes with every other system. The power budget of the lunar base is a constant constraint on what can be done when. During the lunar day, solar panels supplement the reactor output. Peak power production during the day allows energy-intensive operations like ISRU electrolysis to split water into hydrogen and oxygen to run at full capacity. During the lunar night, the reactor runs at its rated capacity and the base operates in a reduced energy mode. ISRU may be curtailed, some science instruments powered down, temperature set points adjusted. Power management requires real-time monitoring and optimization. If an unexpected power draw occurs, an equipment malfunction that draws more current than expected, a system running a startup sequence that temporarily spikes the load, the power management system must balance the load across available generation to prevent a trip that could take down life support. Redundancy in power systems is therefore critical. A single reactor that fails takes down the base. 2 reactors, each capable of supporting minimum life-critical functions alone, means that a failure of one does not create an immediate emergency. But 2 reactors means twice the mass and cost to deliver. The compromise most likely to be implemented for early lunar bases, 1 primary reactor with a backup system, possibly a smaller emergency reactor or a battery bank, that can sustain critical life support for a period sufficient to allow emergency procedures or repair. Battery technology for lunar environments. The lithium-ion batteries that power most terrestrial applications degrade rapidly at the extreme temperatures of the lunar surface. Specialized battery chemistries, solid-state batteries, certain nickel-hydrogen or silver-zinc chemistries can operate across wider temperature ranges. The development of batteries that can survive temperature cycles from -240 degrees Celsius in permanently shadowed crater environments to well above zero in heated equipment is an active research area. Thermal management of electrical systems. In the vacuum of the Moon, there is no convection. Heat can only leave a system by radiation. Thermal management of electronic components generates heat that must be dissipated by radiator panels pointing toward the cold of space. The design of these radiators, their area, their orientation, their thermal coupling to the electronics they serve, is a significant engineering challenge. During the lunar day, radiators facing the Sun receive solar input that reduces their effectiveness. During the lunar night, they can radiate freely to the cold sky. The cycle of varying thermal conditions creates a design requirement for radiators that function across both regimes. Let us now talk about what is perhaps the most important single insight that emerges from everything we have discussed, about what the lunar experience reveals regarding the relationship between difficulty and value. Nothing about permanent lunar presence is easy. We have gone through this in detail: the radiation, the dust, the 300-degree temperature swings, the physiological deconditioning, the psychological isolation, the engineering complexity, the medical limitations, the economic constraints. And yet, the scientific value is real. The practical value as a stepping stone is real. The insurance value for civilization is real. The pattern here is one that recurs throughout human history. The most valuable destinations have rarely been easy ones. The high passes that connected ancient trade routes were difficult and dangerous. The sea routes opened by European explorers were deadly to a significant fraction of those who sailed them. The first ascents of major mountain peaks cost lives. The early aviators died at extraordinary rates. The Moon is not uniquely dangerous in this history. It is one more instance of a pattern where access to something valuable requires accepting real risk and sustained hardship. What is perhaps different about the Moon is the scale of preparation. The Apollo missions sent people to the Moon with a level of engineering rigour unprecedented in previous exploration, and still lost Apollo 1 in a pad fire and nearly lost Apollo 13. The Artemis missions will be even more rigorously prepared. The first permanent base will be designed with more safety margins and backup systems than any previous human outpost anywhere. This does not mean safety is guaranteed. It means that the specific risks are known, characterized, and addressed to the extent current technology allows. The remaining risk, the residual risk after all mitigation, is accepted knowingly by the people who go. This informed acceptance of known risk is different from the unawareness of risk that characterized early exploration. The Apollo astronauts knew they were taking risks, but many of the specific risks we now understand were not well characterized in 1969. The first permanent lunar residents will know the dust toxicity data, will know the radiation dose predictions, will know the bone loss projections and the countermeasures, will know the psychological risk factors, and have pre-prepared strategies. Knowledge does not make the challenges smaller, but it makes responding to them possible. Let us now talk about the specific moment that will define the beginning of true lunar habitation. Not the first landing of Artemis, which will be a short visit, but the first time a crew stays on the lunar surface long enough that returning to Earth is not a near-term option. This threshold, call it the first lunar overwintering, analogous to the first Antarctic winter rovers, is when all the challenges we have discussed become non-optional realities rather than theoretical concerns to be planned for. The first crew to spend a month or more on the lunar surface will experience things that no one has experienced before. The psychological weight of a 2-week lunar night, during which the base is your entire world. The accumulation of minor irritants, suit smell, food monotony, equipment noise, interpersonal friction, over weeks rather than days. The first experience of a solar storm warning requiring the crew to spend hours in the most shielded part of the base doing nothing while waiting for the all clear. They will also experience things that are not hardships but that no one has experienced before. Watching the Earth go through its phases over the course of a month from a fixed point in the lunar sky. Observing the lunar surface undergo the extraordinary lighting change of a 14-day sunrise. Watching the Terminator approach, watching the shadows shorten over days rather than minutes. Seeing stars without any atmospheric interference for weeks at a stretch. The first crew to live through a complete lunar month, one full cycle of day and night and back to day, will know something about the Moon that no previous human has known. Not as a fact extracted from instruments or inferred from telemetry, as lived experience. This is the difference between exploration and habitation. Exploration visits, habitation inhabits. And the first inhabitants of the Moon, whoever they turn out to be, whenever this happens, will carry back to Earth a knowledge of what the Moon actually is, that no instrument, no robot, no remote observation can fully convey. That knowledge will change how we think about the Moon and how we think about Earth. And it will inform every step that comes after: Mars, the asteroid belt, the moons of Jupiter, the far reaches of a solar system that begins, right now, on the surface of a world 3 days away. Go outside tonight. Find the Moon. Look at it for a moment. That is where we are going. Go outside tonight. Find the Moon. If it is visible, just look at it for a moment. You do not need a telescope. You do not need binoculars. It is the brightest object in the night sky after Venus, and it is close enough that you can see its surface features with your naked eye. The dark plains of ancient lava flows, the lighter highlands, the suggestions of crater rims along the terminator where the shadows are longest. 3 days away. That distance is almost insulting in its smallness compared to the rest of the solar system. Mars is 6 to 9 months away. Jupiter is years away. The nearest star is tens of thousands of years away at our current speeds. And yet the moon, our moon, the one that controls the tides, that lit the nights of every human who ever lived before electric light, that 12 people have walked on, is 3 days away. Right now on that surface, minus 100 or plus 100 degrees, depending on where you look and what phase the lunar day is in. Absolute vacuum, complete silence. Regolith that has been sitting undisturbed for millions of years except where meteorites have moved it. And scattered across 6 specific locations, the descent stages of 6 lunar modules, 2 rovers, flags, equipment, footprints that may still be visible, left by the last people who were there. In December 1972, more than 50 years ago. We are going back, not to visit for a few hours, to stay, to build something that lasts, to learn what it actually means to exist there, not in the hours of an EVA, but in the weeks and months of a life. And that, as we have spent tonight exploring, is harder than it looks from here. The dust that is not dust in any familiar sense, but shards of glass that infiltrate everything, that carry an electrostatic charge, that are toxic to lung cells on prolonged exposure. There is no solution to the dust problem. There are only mitigations that reduce it from catastrophic to manageable. The radiation that arrives constantly from all directions, from the galaxy, from the sun, with nothing to stop it. No magnetosphere, no atmosphere. On Earth you receive about 3 millisieverts per year from natural sources. On the lunar surface without shielding, about 380 millisieverts per year just from galactic background, and potentially a lethal dose during a major solar storm if caught outside without shielding. The gravity that is too low for the human body's evolved physiology. Not too low to walk, but too low to maintain bone density and muscle mass without constant active countermeasures. 6 months in 1/6 G and you return to Earth with a more fragile skeleton than you left with. The temperature that swings 300 degrees Celsius between the lunar day and lunar night. The same surface, 300 degrees different over 2 weeks. No material endures that cycle forever. The psychological weight of 2 Earth weeks of continuous day, followed by 2 Earth weeks of absolute night. Of a sky that is always black. Of a surface that is always grey. Of a silence that is not quiet but total. Of Earth hanging motionless in the sky. Everything familiar, concentrated in one small blue disk that you cannot reach for days. None of this is unsurmountable. Each challenge has a path toward a solution. The radiation can be shielded against. The dust can be managed. The physiological effects can be partially counteracted. The psychological challenges can be prepared for. But the path requires honesty about what is actually there. The moon is not a gentle stepping stone, waiting patiently to receive us. It is a world, a genuinely alien world that happens to be close. Its closeness does not make it friendly. It makes it the first place we will have to confront what it actually means to exist beyond the biosphere that made us. Everything that makes life on the moon hard is something Earth gives us quietly, without asking credit. The magnetic field that deflects radiation, the atmosphere that moderates temperature and scatters light and carries sound, the gravity that keeps our bones strong, the biosphere that fills every moment of sensory experience with colour and sound and smell and life. The diurnal cycle that synchronizes our biology. Earth gives all of this, has given all of it since before our species existed, and asks nothing in return. The moon gives none of it.
And so we must bring it with us, in sealed modules, in spacesuits, in carefully engineered life support systems, in psychological training and medical protocols and spare parts catalogues. The people who will first live there, whoever they are, whenever this happens, will carry Earth with them in the only way it can be carried to the moon, in the technology they bring, in the knowledge they have accumulated, in their own bodies. They will be Earth's ambassadors to a world that does not want them and does not know they are coming. And they will make it work. Not easily, not without cost, not without some suffering that could not be planned for.
But they will look out at the black sky and the grey surface and the Earth hanging over the horizon, and they will know something no one has known before. What it is to live somewhere that is not Earth. What it means to sustain life in a place where life is not natural. That knowledge will come back to Earth with them, and it will change how we understand what Earth is, by showing us what Earth is not. Look at the moon one more time. It is 3 days away. It is waiting. It will be harder than it looks.